Welcome back to our C++ for Parallel C++ course for scientific computing. Well, last time we talked about the structure of the standard template library. We introduced things, we tried to lay out some design criteria that allowed us to come up with an explanation why the standard template library is the way it is. Some structure emerged. We realized that the containers exposed by the standard template library actually are very uniform in terms of their interfaces, which allows to build a very uniform and a straightforward structure, and allows us to work with it in a straightforward way, because we don't have to understand everything in order to do something, but just looking at some small examples gives us the idea how we can use the whole thing in various contexts. Today I want to continue that discussion, but I will focus not on the containers like last time, but I will try to talk about some algorithms, and I will focus on what's called iterators and ranges, because that is another concept that is very important in C++ and will help you to understand how to build parallel algorithms later on, and so on and so on. Okay, so we have seen, as I said, many containers share similar operations, insert, erase, and all of them have the same interface for different containers: vectors, lists, maps, sets, hash data structures. All of them expose the same interface. On the other hand, every container exposes a companion type, which is called an iterator, that allows to navigate over the elements that are stored in that container. Again, all iterators have the same interface, and we will see that today, and I will drive that message home today in a very repeated way. The library as such exploits these similarities by exposing generic algorithms, and we start looking at generic algorithms. We've been using them. We used sort, we used unique, we used copy, we used for each, and so on and so on. And all these algorithms, as we discussed, don't know anything about the container type they are working with. So you can apply any of those algorithms to any of the containers. And on the other hand, if you write your own container that follows certain patterns, you can use all the predefined standard algorithms with your containers as well. That picture we saw last time, which gives you kind of the structure of the standard template library. And we see that we have three parts in there. We have the algorithms. And as I said, the algorithms don't know anything about the containers. We have the containers, which on the other hand store the data, but don't know anything about the algorithms. And the connecting piece between the two are special types that are called iterators. You might think, why is that so special? Well, if you look at how other languages do that, Java, for instance, if you know Java, you will remember that you have all the data types, you have all the containers there as well. You have lists, you have sets, you have arrays, and so on. But all of them have their own algorithms defined. So you have list.sort, array.sort, set.sort, and so on and so on. So each of those data types has its own algorithms implemented. In other words, you have m times n algorithms implemented, if m is a number of a vector of containers and n is a number of algorithms. Here in this case, you don't have that proliferation of algorithm implementations, because you have one algorithm implemented that is usable with each of the data types. They are completely independent, which reduces the amount of code that needs to be written to have a full set of facilities by orders of magnitude, as you imagine, right? If you have one sort algorithm or one unique algorithm that works with any container, then you don't have to, well, then you don't need one special for each of the algorithms. And that is a real benefit. You have that orthogonality between between containers and algorithms, which is so fundamental and very unique for for C++. As far as I know, no other language or no other library for any other language follows that path. Okay, so let's talk about iterators. What are iterators? In a general sense, you can think of an iterator as some type, some reference to an element inside a container. I'm referring to an element in a container, and I can do things with that element. There are more general purpose iterators, and we will see some of them today, but that's the general notion. If you have some C knowledge and have done some C work, you know what a pointer is. And a pointer is nothing else but a special type of iterator. And as we will see, iterators are modeled after pointers because they support the same operations as a pointer supports. But let's start in the beginning. We usually deal with ranges which are sequences of elements. And those ranges are delimited by some begin iterator that refers to the first element in the sequence, and a end iterator which refers to the first element after the last one. And we discussed briefly last time why that's done. So we are always, when we're talking about pairs of iterators delimiting a range, this is always an open range. The last element, or the element the last iterator refers to, is not part of the range anymore. This is done for the reason to be able to represent empty ranges, because with when you have an empty range, begin and end both refer to that non-existing element, which wouldn't be possible if you had if the end iterator was referring to an existing element. Then how would you represent an empty range? That it wouldn't be possible. By the way, this is true also not only if you refer to a full container where begin refers to the first element in a container and end iterator returned from a container refers to some non-existing element. This is true in for all contexts where ranges are being used. I can represent a subsequence of a container as a range from begin to end, and even in that case, the element the end iterator refers to is not part of the range. So what is an iterator? Just very broadly speaking, an iterator is a type that supports the iterator operations. Nothing more, nothing less. And there are three operations we highlighted last time, and a iterator has to support, and any type that supports these operations can be used as an iterator, as we will see today. The three operations are increment. That means, okay, the iterator points to that element. When I increment the iterator, it will refer to the next element in the sequence. It just will move one element forward, which is the same as pointer and increment, right? If you increment a pointer, it just moves to the next element after the one it was referring to. Star, and I mean the unary star, so not the multiplication operation, but the star that comes in front of the variable, is used as a dereference operation. It gives you it refers to the value of the element it currently is currently pointing to, and equal is comparing iterators and will return true if two iterators refer to the same element. It doesn't mean that the iterators themselves have to be equal. It just means that they refer to the same element inside a container. As we will see, there are some iterators that support more powerful operations, for instance, minus minus, which obviously just allows us to go backwards through a sequence, plus, which allows us to jump not only to the next element, but to an arbitrary element in the sequence by doing plus n or minus n, and the indexing operation, which allows us to use an iterator as if it was an array. But again, these operations are all modeled based on what you can do with a pointer. So the pointer is kind of the proverbial parent of all iterators. Let's look at some generic algorithm and how do generic algorithms actually use iterators to do what they are supposed to do, and why are they completely independent of the containers they operate on. Let's start with copy, because copy is one of the simplest generic algorithms. Obviously, it's not part of any container, but what it does, it copies all elements that are given between the first two arguments, which refer to a source region, and they will copy the elements to a sequence that starts at whatever is given as a third argument. So a copy is invoked with three arguments like this. You write copy begin and out, where begin and end marks the sequence you want to copy, and out marks the beginning of a new sequence. If you look at the implementation of copy, you will see that in the end it's a simple loop. Again, to get back to Panos, why do we use functions that in the end are just glorified loops, and not even a for loop in this case, it's just a while loop, so it can't be easier than that. And as you can see, it will go over the sequence from begin to end and will copy whatever begin is referring to whatever out is referring to, and afterwards it will increment the two iterators. So it will repeat that loop until begin gets to be equal to end. Just for those who have never seen that a bit complicated expression, star out plus plus equals star begin plus plus, this is just a shorthand of saying dereference begin, assign whatever it returns to the dereference out, and increment things afterwards. Have you talked about pre-increment and post-increment in C++? I don't remember if you talked about that. Everybody knows what the difference between pre-increment and post-increment in C++ is? Who doesn't know that? Python has it. But anyway, the difference is the following. When you have a variable I, well, let's say it's an integer. Integer I equals 42. And I say integer j equals plus plus I. That plus plus stands in front of the variable and means pre-increment. So what happens is I will be incremented, and whatever the result is, it will be assigned to j. So after that operation, both I and j will be 43. I because it was incremented, and j because the assignment happened after the increment operation. Whereas when you write integer k equals I plus plus, then I will still be incremented, but k will be assigned the old value of I because it's taking the value first and incrementing afterwards. Okay? So in this context, these are completely equivalent, but as you see, it first copies the sequence or the element and increments it afterwards. I just wrote it the other way around here. In this context, it doesn't make sense because the return value of the increment is not used anywhere. So, okay. If you look closely at this loop, we will see that there are some potential problems there. Anybody sees a problem with that loop? What could possibly go wrong? I mean, it's C++. You have to wear a helmet anyway when you're programming. But what problems could there be? Right? We are passing two iterators, and we are passing an iterator that refers to a beginning of the sequence. And that loop doesn't look whether out actually hits the end of the destination sequence. So what this loop assumes is that there is enough room for things to be placed, actually. So we have to be very careful with that iterator here. We can't just pass some arbitrary iterator and not making sure that the destination sequence is large enough to begin with to hold all the elements I'm going to copy into it. So let's talk about that a bit. What can we do about that? And why is it done in that strange way that copy really blindly copies things to somewhere without checking whether it's a valid operation? Well, one of the purposes to mitigate that issue is to use what's called an iterator adapter. It's called back-inserter. And back-inserter is a function that returns a special iterator. And that special iterator not only copies things, but it makes sure that there's enough room for the thing to copy too. So we use it in that way. Instead of just passing some end iterator or some iterator to our destination sequence, we call back-inserter with our container we want to place things into, and back-inserter will make sure that whenever something is actually being copied into the destination iterator, the vector will be expanded first, and the new element will be appended to the back. That's why it's called back-inserter. Okay, so we have special things that allow us to go beyond referring to an element in a container, but do additional things while we are working on our data structure. So let's have a look at certain scenarios where it actually will not work. So if you write copy button begin, button end, and we pass red where red is a container, why will that not work? Anybody? So let's assume red is a vector of something. Anybody? Why will it not work? What are the requirements for the types of copy? The requirements is that all three are iterators. Then copy will work. Well, red is not an iterator, right? Red is a destination container. So it will not compile because red is not a container, not an iterator, it's a container. What if you write this? If you say bottom begin, bottom end, red.end, will that work? Yes or no? Will it work? Well, the question is, will it compile? Yes, it will compile, because this is now an iterator. But will it do what you want? The answer is no, because if you go back to the loop I showed, the out iterator will always be dereferenced in order to assign things to it. Are we allowed to dereference an end iterator of a container? No, because there is no element there. So this will not work either. So many problems, obvious. Why is it designed that way? Well, there are several reasons. One of the reasons is that separation of concerns is always a good thing. The design separates the notion of copying something from the notion of inserting something in the destination container. The other thing is that none of the algorithms in the standard library change the container itself. None of the algorithms. And that's very important to remember. They might rearrange the order of the elements, or they might change the elements themselves, but they will never change the container. They will not remove things from the container. They will not add things to the container, which is an important notion. And if this was working somehow, then that would imply that copy actually can do something to the container, which it doesn't. The back-inserter we were using was a special iterator which was changing the container, but copy itself didn't do anything to the container. And last but not least, back-inserter can be used not only with copy, it can be used with transform, with many algorithms that actually receive or assume to put things somewhere. Because whenever you want to generate a sequence of elements, back-inserter is your friend, because it can expand the underlying container if needed. Okay, so let's do another example. I have a function f which receives a vector of doubles and a reference to a list of ints, and what it does, it copies the elements from the vector into the list. And as you can see, we can use copy for that just fine. So copy doesn't rely on neither that the destination and the source represent the same container type, because here it's a vector and a list, and it doesn't rely on that the element types are the same. All it relies on is that whatever begin returns is convertible to whatever out expects. So a double is convertible to an integer, so everything's fine. Copy will do what it's supposed to do. The only thing we have to make sure is that the list container actually has enough elements pre-allocated so that copy can put things into it. Again, we don't use backinserter here, so we assume that list already has enough room for everything that will be copied. That's why I added that if statement. That just makes sure that copy will not be invoked if the size of the list is smaller than the size of our vector. Make sense? Good. Okay, while preparing this lecture, I realized that we didn't talk about streaming operations in C++ at all, input-output. I always try to use the print or println to print something to the console, but we never talked in any capacity about streaming I/O. And stream I/O is kind of one of the ways, a very fundamental way in C++ to do I/O, to the console, to files, and in other contexts. So I want to take a side here and introduce that quickly, because we will see that we can connect streams with iterators in a very nice way, and I will give you an example. Okay, so let's assume we want to read a list of doubles from the console, from the keyboard, and we want to compute the median value of those doubles we're reading. How do we do that? Well, we define a vector where we want to put those values into, the ones I'm reading from the console. I'm using a loop, and standard cin represents the keyboard. So the streaming operation, in this case a right shift operation, you can read that as use the console, and whatever the console provides you with, move into the variable x. So kind of shove it in there. That while operation will be successful until it hits something that is not a double, or whenever you hit enter file. Then it will stop doing that. That's why we can use this operation as if it was a Boolean. So that Boolean will evaluate to true as long as the input operation was successful. And it will read one double after another, which are probably white space separated or something like that, or enter or similar things. And whenever I write a value, I just put it back into my vector. I append it to the vector. Then I sort the values in the vector and take the middle element of all the values I read and print that out. And here you have the equivalent operation to cin, which is called cout, console out. Now the streaming goes in the other direction. You can output things to the console just by saying cout, left shift, and whatever you want to do. The interesting thing is that these streaming operations can be chained. So you can have many of those operations on the same in the same output, and input can be chained in the same way. Very simple to understand, but I wanted to explicitly introduce that so that you get the context of what will come on the next slides. Because what C++ also can do, you have streams that represent files. In the same way as you have a stream that represents your keyboard and your terminal, you have special types, stdf stream, that represent files. So what we can do, we can create a new OF stream, which we call out. The argument it is used to construct the OF stream is a file name that will be used. So it will open a file for writing, and then I can stream something into that file, and it will be saved in the file. Please note that whenever the OF stream goes out of scope, at the closing brace of its surrounding block, the stream will be automatically closed. If you took the operating system class or any similar class, they probably taught you whenever you use a file, you have to explicitly close it. In C++, you don't have to do that, because the destructor of that object will automatically close the file, which is nice because you will never forget to close the file. Very similar in Python, right? When the object somehow gets garbage collected, it closes it automatically under the hood. So you don't have, you can call close if you want to enforce it, but you don't have to. Same is true here. So the opposite is, works as well. We reopen the data file now for reading. Read one line with a supplied function from the standard library, which is called getLine. And we get the line back we actually wrote into the file, and we can output that to cout just to verify that. So you can use streaming operations both for input and output in a very similar way as you use it for the keyboard. Another example, there is a stream that actually doesn't write to a file, but writes to a string. So you can do in-memory streaming operations. Example, it's called string stream. I'm streaming something into the stream. Then I pull out whatever the stream currently contains into a separate variable. The closing brace will destroy the string stream because I don't need it anymore. And then I can print whatever the line had, and we will get our hello world. Same scheme. So you can use string streams to stream into it and stream out in the same way as you're using files or consoles and so on. But the best thing of all is that you can define your own streaming operations for your own types. So let's say we have a type x that contains an integer value. Then I can define two operators, the left shift operator, which is a streaming operator, and the right shift operator with two arguments. Whenever a O stream is used with left shift and one of those x's, this function will be called. So whenever I want to write an x to the output stream, this function will be used, and all it does, it writes the value that is stored in the x. The opposite works as well, so you can do that same for the input streaming. Okay, just example how to use that. I want to write two x's to my data text output file, and as you can see, after defining these two operators, I can use x's with my streaming operations in the same way as I can stream integers or doubles or anything else. Same for input. I can read them back in and will get the proper values. Right, I define some default constructed x's, and then I use the input streaming to write whatever I was writing into the file back into my variables. So you can extend that streaming mechanism in any way for your own types, and that is kind of very important. And we will define operators in many contexts in C++, and we will see that this allows us to have that uniform interface for many things. Any questions about that? I know I'm glimpsing over things, but I wanted to kind of highlight that for you so you understand what's to come now. Okay? So back to iterators. What iterators do also is, or what the standard library does, it predefines so-called stream iterators. So it's an iterator that is constructed from a stream, and whenever you use that iterator, it will use the underlying stream to do the operation. So an O stream, when I construct an O stream from cout, that means whenever I assign a value to a dereferenced O stream iterator, it will actually write to cout. So I construct a new O stream iterator, then I assign hello to the dereferenced O stream iterator, which will write it to cout. Then I increment the O stream iterator, which kind of does nothing, but you should do it anyway. It means get ready for the next output operation. And then I write the next one to the stream, to the iterator. The opposite works in the same way. So you can define an iStream iterator, in this case from standard in. And when you read from the dereferenced iterator, it will actually result in a read operation on the stream that is the thing was constructed from. So you can use it with files in the same way. But it's an iterator, and so you can use these things with algorithms, and we will see in a moment how useful that is. So let's create a dictionary. What is a dictionary? A dictionary is a program, or a dictionary generator is a program that reads in a text and spits out a list of unique names of unique words that are sorted on alphabetically or something like that. Let's write that, and you will see it's just a couple of lines of code. So we have two files, the one we want to read the text from and the file we want to write the dictionary to. Then we define a couple of iterators, two iStream iterators, one which is bound to our input stream, to our input file, and an iterator that is constructed as representing the end of file. Right? We want to copy things from A to B, so we have to have an end iterator representing the end of the file, and a default constructed iStream iterator represents that. So we can always use that as an end iterator. We create an OStream iterator to write things to our to.txt file, which is represented by the OStream. And now we can construct a vector, and you might not know that, but you can construct a vector from a range of iterators. So this one line will read in the whole file and will separate it into words and will list all the words, store all the words in the vector from the begin iterator, which is the begin of the file, and the end of the file. So it will read in the whole file. Then we sort our vector in order to get a unique list, a sorted list of words. And then we use an algorithm which is called unique copy, which is exactly what you think it is. It creates it's very similar to the unique algorithm we already talked about. It will reorder elements in a way that only the unique elements will be considered. And instead of doing that in place, like the unique algorithm we had already in the lectures, it will copy the result to the iterator given to it, which in this case is our OStream iterator. So you see that the OStream and the iStream iterator are facilities that allow to connect our algorithm to files and to streams, which is very, very useful. And it also shows you that iterators can be more than just referring to an element inside a vector. They just refer to an element in general, and you can do various things with them. The only condition for these types to work properly is that they support the three operations I talked about. As long as they support dereferencing and comparison, things will work. No matter what you pass to the algorithms, as long as these things support these operations, the algorithm will do what it's supposed to do. Okay, just as an example, let's say we read this file, then this will be produced by the program, and you can try it out. It just does what you expect it to do. Questions so far? Things will get a bit more interesting in a minute. Okay, so let's look at iterators in general, a bit more what iterators are, how they are built, what operations they support. So we said that iterators are special types. They identify a container and an element. They let us examine the value stored in that element. They provide operations for moving between elements, and they restrict the available operations in ways that correspond to what the container can handle. And we will see how important that is in a minute. But they can be much more general, as we have seen, and I will give you more examples soon. First, what we need to do is that all containers expose their own iterators. And since we don't know what the type of those iterators are, because each container exposes its own iterator types, they're exposed through these embedded names, so you can always write std vector double : iterator, and it will give you the type of that iterator, so you can work with it. We don't see the actual type. We just know what that thing can do. Namely, it can do the three operations. Okay, so let's talk about these iterate operations in more detail. As I said, containers do not expose their specific iterator types, but you can actually ask the container for its begin and for its end iterator. You can compare iterators, as we said, and you can increment iterators, which makes the iterator point to the next element in the container. You can dereference them, which gives you a reference to the element they refer to. By the way, you can use them in the same way as a pointer. So if you're referring to a struct which has a name member, then you can just refer to that name member of the element the iterator refers to by writing it this way. So you have to write parenthesis star dot name. Why do I need the parenthesis? Anybody? Well, the precedence of the dot is higher than the precedence of the star, so I have to turn it around. Otherwise, if I write it this way, it will try to dereference the whole thing. That's what we don't want, right? So example, if I have a struct x that has a name in it and a vector of those, then iterator refers to one of those x's, and if I want to get to the name, I just have to write it this way. But you could write it this way as well, as with a normal pointer. The same way as you are used to work with pointers in C, you can do with with most of the iterators. So this and this is completely equivalent syntactically. You can choose which way you want to go. Interestingly enough, some iterators are more powerful than others. I said normally an iterator can be incremented only to the next element, but some of the iterators can actually do more. They can be incremented by a certain amount by a certain value of I. That means it will jump n elements ahead or n elements back, which is completely equivalent to invoking ++n times. But since some containers support jumping around like a vector, right? It's an array. So when I refer to one array element, I can easily go to the element that is n steps away from the current one by just adding n to the underlying pointer. So the operation +n is much more efficient than calling ++n times, which would impose a loop and had a complexity of O(n). These iterators are called random access iterators, and they are exposed by random access containers, and we will see that in a moment. Okay, so that tells you that there are many different iterators, and they are combined in concepts. And here are the concepts that iterator represent. In the simplest case, like we've seen in copy, it could be an iterator that reads one item at a time and needs to forward in one direction only, right? Copy just goes ++ through the sequence. Those things are called input iterators. On the opposite side, there are things that called output operators that write things one at a time and forward only in one direction. The out thing that copy was receiving is a very minimal output iterator, right? It doesn't need to support anything else but writing to it and doing ++. If you combine these two, you get to a concept that is called forward iterator, which means you can read and write through the iterator. For instance, if you get an iterator from a input stream from the keyboard, you can't write to it, right? Nobody can write anything to the keyboard, or you can't read anything from the terminal. That's why the keyboard is represented by an input iterator and the console is represented by an output iterator. Whereas when you have something more powerful, a container underneath, you can read and write to it. You can change the element the iterator is pointing to. There are bidirectional iterators that can go in both directions through your sequences. If you have a bidirectional list, you can not only go to the next element, you could go to the previous one. And last but not least, there are random access iterators that can read one at a time, forward and backwards, but can jump to arbitrary elements inside the container as well. So let's look at the operations these iterator types have to support. Input iterators have to support ++, reading through the dereference and comparison, and the concept is called standard input iterator. Output iterators are similar, except that they only write through the dereferencing. Forward iterators support both reading and writing. Bidirectional ones support additionally to be decremented, which means they can move backwards through the sequence. And random access iterators additionally support ±n indexing Yeah, these two operations additionally, and they are called random access iterators. If you look at what containers in the standard library support what type of iterators, you will quickly realize that there is a thing that is called forward list, which is nothing else but a list that is a single linked list, right? It has only a reference to the next element in it. That means the iterators exposed by that container can't go backwards because there's no way to figure out what is the previous element. The container knows only what its next element is. Bidirectional iterators are lists, which are bidirectional lists. A map, a tree, is usually a bidirectional data structure because you can go backwards and forwards. And last but not least, arrays and vectors are random access because they represent a contiguous sequence of elements in memory. Here's just a table summarizing this to give you some idea which container supporting which type of iterators. So I think we are now at the point that we can start looking at more generic algorithms. And I want to give you another example here, just to introduce a couple of more algorithms that we haven't seen yet or haven't talked about yet. As an example, to give you a kind of sense what is actually available in the standard library. So let's assume we have a string S which contains a bunch of words, and I want to split the words that are in the argument and return a vector which contains all those strings. We have seen one way of doing it. I will do it a bit more differently. In this case, a bit more complicated, but bear with me, we will get there. So we want to create a vector of words, which we will return in the end. And we want to go over the whole sequence of the input string until we reach the end of the input string. How do we find a word? Well, we start at the current position and loop over the input as long as the current character is a white space. Because we are not interested in white space, we want to go to the first non-white space character. Once we found the first non-white space character, we continue looking for the next white space character after the words, which allows us to separate that word between, because it's usually between white space, right? And once we have that, we can extract that substring because it goes from I, which is the beginning of the word, and j minus I is the length of the word. So we can extract that from our string and add it to our vector. That looks awfully difficult and awfully error prone, as you can imagine, because writing loops is never a good idea. So let's try to replace those loops with some existing algorithms, which will simplify our task a lot. So how do we find the first character that is not a space? Well, we use a standard algorithm. Find if, start looking at the current position, go to the end of the thing, and stop at the first character that is not a space. We found that. Now, do the same, start at I until the end, find the next thing that is actually a space, right? Once we have that, we found our word. So we can do the same as before. And now it's much more compact and much more easy to understand what it's actually doing, because you don't have to understand what the loops are doing. You just look at the algorithm. Okay, find if, not space. I know what it's doing. And it will return an iterator that refers to the first character that is not a space. Here are the predicates I was using. Not space is just returning whether the argument is not a space, and space is a predicate which is returning whether it's a space character. And you can certainly use a lambda for that. No problem, right? So instead of having that extra function, we can just drop a lambda in there, which is doing exactly what we want. Another example, palindromes. Everybody knows what a palindrome is, right? It's those words that you can read backwards and forwards, and they will result in the same word, like level, high, civic, and so on and so on. So how do we find them? We write a function as palindrome, and we use an algorithm equal that starts at the beginning and the end, and looks at another, well, equal compares two sequences. One sequence specified by the pair of iterators that are first, and a sequence that starts at the third argument. Please note we have two new constructs. One is equal, which is the algorithm, just comparing two sequences. But that thing, rbegin, is noteworthy. It's not a typo. It's just really rbegin. So what is rbegin all about? rbegin gives us an iterator that points to the last element, and when I increment it, it will go backwards through the sequence. It's a reverse iterator. It does the opposite thing. So that our code we had here essentially starts at sbegin and at rbegin, which is at the end, and will compare characters as you go, and will tell you whether these characters match. So it will return true if those two sequences are equal, which means that I can read the word backwards and forwards. So rbegin is another example of an iterator that allows to do more complicated things than just referring to an element. But the trick is you increment it and it goes backwards. Rend is the opposite thing, which points to the first element before the begin, just to match the sequence so you can use it. So equal itself, as I said, is a standard algorithm that takes two sequences from begin 1 to end 1 and compare it with a sequence in begin 2. But there is also a version that actually allows you to specify the begin and end of both sequences explicitly if you're interested. But if you think about it, our palindrome function actually does more work than it needs to, because we can stop when we hit the middle. Right? When we're at the middle and things are still equal, then continuing to compare things is not necessary anymore. So what we do instead, we move the begin iterator to the middle of our sequence and use the middle of our sequence as the end of our comparison operation. I'm using advance for that. The reason is that advance knows what type of iterator it is being applied to. If it's being applied to a random access iterator, it will do plus equals n. But if it's applied to something else, it will use a loop and will increment the iterator n times, because other iterators don't support plus equals n. So advance is another algorithm that is specific and knows what iterator types it works with and can be optimal for any given iterator type. Okay. Let's be a bit more specific when we look at copy, because this is our copy implementation. And just to make copy a bit more safe, what we will do, we, instead of not constraining our iterator types, we specify that copy actually has to work with an input iterator and with an output iterator in order to compile, because otherwise I might be able to call it with something that is not an iterator, and I will get very strange compilation errors. But if I constrain the concepts that are the type properties our arguments require, we can get much better compilation errors if we make a mistake. Okay. One thing I want to do, and that is really an interesting use case, is for each goes from begin to end and calls our lambda for each of the elements it receives. It iterates over. But this will not work if I specify 0 and 10 as the arguments to for each. Why will it not work? Anybody? What does for each expect? It expects two iterators to be passed to it. Here I'm passing integers and not iterators. So this will not compile, as the algorithm expects a type that conforms to the concept of an input iterator for its first two arguments. That means that the type needs to support what? 3 operations. It needs to support plus plus, it needs to support dereference, and it needs to support comparison. Well, an integer supports 2 of those operations, but it doesn't support the dereference operation, right? We can't dereference an integer. That's why this will not compile. So let's make it happen so that we can use indices with our algorithms, because sometimes that's very useful. If you have a normal loop with I from 0 to n, you want to replace that with a standard algorithm because you want to parallelize it or something like that. And in those cases, you have to do additional things because you can't just drop in, replace all the arguments with a standard algorithm because of that iterator constraint. So let's create an iterator type that represents an integer counter and that returns the current value of the integer when it's being dereferenced. Okay? So we need a type that exposes our iterator interface. It represents an integer. It returns that integer when dereferenced. It increments that integer when being incremented, and compares the integer with the integer contained in another iterator when compared with another iterator. So let's create that. We don't want to constrain things to integer counters, so I'm just making it a template which will work with any integral type, with anything that is an integer, int, long, unsigned long, whatever you want. It has to represent an integer, so I'm storing the integer in the type. I need a dereference operation, right? We said whenever it's dereferenced, return the integer itself. And the dereference is implemented by the operator star. Again, as we can see, our types we define in C++ can expose essentially any operations. They can define functions that will be used when a certain operation is applied to that type. So whenever I apply a star, a dereference operation to an instance of my counting operation, this function will be called. So whenever I dereference a counting iterator, we will get the value of the current integer. Prefix, increment. Well, operator plus plus, what does it do? It needs to increment our integer, obviously, and it needs to return a reference to itself so that you can chain things. Easy. How do we represent the postfix plus plus in C++? What does the operator look like? When this is a prefix operation, but we want to implement postfix because we want to be able to write iterator plus plus to do postfix. Well, the trick C++ uses is it says there is a dummy integer argument which is never used, which has probably a value of 0 or of something, but whenever a postfix is being needed, this operator is being called instead of the other one. So we can define both operators, which gives us the prefix and the postfix plus plus for our iterator. And last but not least, we need to compare them. We get two iterators, and when we want to compare these two iterators, we have to compare the integers that are stored in that iterator. Done. Well, we need to construct it. Just a constructor that allows us to initialize things with something that is not 0 if you want to. But this is your counting iterator. So once we have implemented that, we can now write this. We can now say for each counting iterator 0 to counting iterator 10, do call my lambda. And it will do exactly what we expect. So it's a very nice way when you want to convert a normal loop that goes over a range of integers into something that is something that uses a standard algorithm. And since counting iterator is a real iterator, you can use it with any standard algorithm, as long as it conforms to the operations you want to supply. So this will come in handy over the course. That's why I wanted to introduce that today, because we will use it occasionally or for code I'm showing here in the lectures. And whenever you read counting iterator, you will know what it does. It represents an integer which converts it into something we can use with standard algorithms. Again, another example that shows you how powerful these iterators are. You can easily define your own. It's trivial once you know what to do. And that allows you to use the predefined standard algorithms, which were written in 1995 probably, before most of you were born. But you can write your own classes and use it with them. Isn't that great? This is the real power of generic functions in C++, that you combine things, everything is orthogonal, and you can extend it in a way as you need it for your application. Now, I want to talk about ranges because that extends beyond iterators slightly, but it's still a very useful topic. I want to talk about these concepts. What are ranges? Well, Ranges are in general sequences of elements. Not a single element like an iterator refers to, but a range refers to a sequence of elements. In the simplest case, a range is a pair of iterators. So begin end gives you a range of all elements between begin and end. But a range could also be a counted sequence. It could be something that starts at a certain element and tells you how many elements you have. It could be a conditionally terminated sequence. It could be something that starts somewhere and has a predicate that tells you when the sequence has reached an end. A C string, for those who know what a C string is, a string in C, it's a sequence of characters that is null terminated. So in order to be able to use C strings with standard algorithms, you would use a special range that has a begin and the null terminator as the end condition. And that would allow you to use C strings, C-style strings, with all the facilities we have. And certainly there could be unterminated sequences that will go forever if you don't stop them. The standard library has special versions of the algorithms in the ranges namespace, which allows us to pass ranges as a first argument. So instead of having source.begin, source.end, I just specify the range I want to work with. And the container is a range, right? It represents all elements that are stored in the container, which simplifies things a lot, because now I can really express what I want to do. I want to copy everything from source into my destination container. And I don't have to deal with that begin and end explicitly. Okay, so what is a range formally? A range is a type that supports two operations, begin and end. That's it. And begin and end are supposed to return iterators, or something that conform to the iterator concepts. So anything that has that property is a range. Similar to iterator categories, we have range categories, which are defined by the iterator they depend on. Right? Each range has somehow one iterator hidden behind it. So the category of that iterator behind the range is the category of the range itself. I have input ranges, output ranges, and so on and so on. Okay, let's use these range algorithms. Let's say we want to take a sequence of integers and we want to double all even numbers in that sequence and want to generate a sequence that has those doubled numbers in it. So we start off with a vector of 1, 2, 3, 4, 5. We use copyIf, which is yet another algorithm from begin to end. And the criteria is copy things if it's not even. No, copy if it's even, right? When that predicate returns true, then the input value will be copied to the output. If that predicate returns false, the value will not be copied. So we have now a sequence of even numbers in our vector, even numbers. And what we need to do now, we need to double them. We use another algorithm, transform. Transform goes over all the elements of a sequence and calls the predicate or the function for all elements and replaces whatever the value was with whatever the function returns. So transform will go over all our even numbers and will insert the result of that function for each of the numbers, which in other words is just the doubling of our even numbers. And now we can print them. We print them to the console. This is not very nice code because A, I'm using begin and end, and B, I create intermediate vectors, even numbers, results, which are not needed for anything, because I could just go over it and double the numbers if the conditions are right. So let's rewrite that in a more efficient way and in a more flexible way. The algorithm copyIf takes a pair of iterators, so wouldn't it be easier to just pass numbers to the algorithm? So that's what I did here. CopyIf numbers, and please note I'm using the algorithm which is in the ranges namespace. And now I don't have to supply begin and end, but I can supply an arbitrary range as the input. The same for the transform, and I get the same result just by using the different algorithms. But it's much easier to read and write because I don't need that begin and end notation anymore. I just pass the whole range into the algorithm. So that's one thing. The standard library gives you a set of all the algorithms that are defined in before are also defined in the ranges namespace, but they expect ranges wherever pairs of iterators are needed for the other set of algorithms. You can use it for yourself in any context. Just try it out. The other thing is that, as I said, the even numbers have to be stored separately, and the result has to be materialized explicitly as well, which is not good because if our sequence is very long, why do we store these intermediate results in memory and waste memory and time and whatnot? So, as we have seen, the iterator-based algorithms are very flexible, but they don't compose well. So what can we do? The standard introduces another concept which is called a view. View is a data structure that refers to a range that lives external to the view. It doesn't own the data. It really just represents it and allows you to look at a sequence of elements from the distance. So there are adapters that allow to iterate over a range and possibly change things and possibly apply additional operations. In that sense, they are lazily evaluated. They produce a value only when explicitly asked for the value. So the value will not be eagerly produced as in our algorithms by putting them in a vector, but using views allows us to do the same thing without storing all the intermediate values over and over again. So how does that look like with ranges, with views? We start off with a view which is called iota, initialized from 1, which means please produce a sequence of integers starting at 1. As long as you're being used, as many integers you will produce. Now pipe whatever it produces into a special view that will produce 5 results only. Take the first 5 results you ever get. So it will constrain our iteration to the sequence of numbers from 1 to 5. Then we filter whatever we get by applying that predicate. So please apply the predicate, and if it returns true, the value will be forwarded, and if not, it will not be forwarded. And last but not least, we transform it by multiplying with 2. So what we have here is absolutely the same code as before. And those who know Linux, can understand what the pipe does. It essentially means produce something, feed it into the next one, feed it into the next one, and so on. And the result is stored as a range, which is called results. And that range doesn't even contain any data. It is really just a recipe to generate things, nothing else. And now we can just use our results and iterate over it in the way we always do and print the result. And only while things are being iterated, that thing is being evaluated for each of the values it should produce. So views are very powerful because they allow you to compose algorithms in a very nice way. Play with them. You will love them if you start playing with views because they are very natural and very straightforward to apply to many algorithms, especially when you have to combine sequences of operations where one operation has to produce some intermediate value which you don't need anymore, then views are the way to go, definitely. So this just explains what I just said. The results object composes the 4 operations. Iota, which in each iteration returns a new integer. Take signals to be at end after a given number of iterations. Filter calls a given lambda for each value and decides whether it will feed on the current value to the next stage or not. And transform will apply a function to generate some new value based on the input value for each iteration. So this is very composable, as you can see. The ranges are still iteratable, still based on iterators under the hood, but those are not exposed. And no intermediate unnecessary values have to be stored because everything is generated on the fly while you are iterating over it. If you want to use views to do the same as what we were doing with our counting iterator, it's very simple. We just use ranges for each. And instead of using a pair of counting iterators, we just tell it, iota 0, take 10, and that is our counting iterator. Very same code will generate the sequence as before. So you see that whatever the views produce are ranges in the context that they can be passed to the standard algorithms directly. So all iterator-based algorithms have a corresponding range-based algorithm in the standard library. The only difference is that they live in a different namespace, standard ranges in this case. So if you want to use range-based algorithms, you have to use std ranges instead of just the std namespace. And as you see, there's no need for begin and end. It simplifies using ranges, containers, and so on and so on. Just a list of ranges, range views that are available, and there are many more. Just to give you an idea of what are the predefined views, you can easily define your own views if you have special needs, in the same way as we were creating iterators. But the views are, just go through the list, read the documentation. You will find a lot of interesting things for your needs. The last question you might have is, what about parallel range-based algorithms? Right? We were introducing, or we were talking last time about that all these standard algorithms have parallel versions where you just use std execution par as the first argument, and the library will parallelize things. Well, unfortunately, C++ standard library does not have any range-based parallel algorithms. They are not in the standard. They are being discussed, but people don't, well, nobody has managed to get it through the standardization. Standardization is a process which is very bureaucratic. So if you want to get something into the C++ standard, you have to write a paper that proposes what you want to do. Then you go to the standardization meetings. If you're lucky, you might be able to present it to some group of people in the standardization meeting. They would start ripping your proposal apart, will send you home so that you can come back next time with a better proposal. That iteration has to happen 2 or 3 times until everybody's happy. And then it moves to the next group of people in the standardization, which will do the same thing to you. That's why standardization usually takes years for something from an idea to get it into the standard. And nobody has managed to get the parallel standard, the range-based algorithms into the standard that way. We didn't want to wait for it. So what we did, we just implemented them in HBX. So what HBX gives you is, for all algorithms that we have in the standard, it gives you a range-based algorithm which actually accepts the parallelization policy as a first argument. So if you want to use standard-based parallel range-based algorithms, you can do that with HBX easily. So there we have really tried to be very orthogonal. So for everything that exists in the standard, we have that, and we have a bunch of extensions that allow us to represent parallel range-based algorithms in an easy way. So if you want to take advantage of that, that is available to you there. So all algorithms in HBX have their range-based counterparts, and that is true for all the parallelization policies and for all the algorithms. Okay, any questions? I know it was a lot of information today, kind of whirlwind through the whole story of iterators. And I will not get back to that because I don't want to bore you. But I thought that it might be interesting and important to lay the groundwork, because that will help you to understand many things we will do in the future with iterators. And especially we will use that counting iterator over and over again in various contexts where appropriate. Okay, well, thank you so much. One last announcement. I will have to cancel next week's Thursday lecture. So we will have a lecture this Thursday, next Tuesday, but the lecture next week's Thursday will be canceled. Okay? Thank you so much.